Hello everyone, welcome to IMS GATE Academy. As we are discussing our foundation course on fluid mechanics, we have completed our kinematics part, and before that we have discussed the properties and the statics part also, right? Now in the dynamics part, the most important part like Bernoulli's equation, Navier-Stokes equations, all those things we have already completed, right? Next, the point is what the laminar flow, very important chapter of entire fluid mechanics, and from which you will see highest number of questions also in the gate examination, right? We'll discuss the laminar flow, okay? Laminar flow or viscous flow we can say. All those things we'll be discussing here today. Okay everyone, now see. Right, so what we'll be discussing, the laminar flow. Laminar flow through pipes. Specifically we'll take a circular pipe. Right. Okay, so what I will take here, first of all, a small fluid element I will be taking, and in that I will be discussing the forces that is going to act over that particular fluid element. Okay, then we'll see how much is the pressure gradient is there. We'll calculate the pressure gradient in that particular fluid element, right? Now everyone see. So let's suppose this is let's suppose your pipe. Right, and let's suppose in this I'm taking in a small fluid element I'm taking. Small fluid element I'm taking, right? So now very important point you need to understand. On this face some pressure is going to act, and on this face also the pressure is going to act. So let's suppose this element length we can consider as dx. The element length, fluid element length I am taking as dx. So P plus dou P by dou x into dx. This is what the pressure that will be acting, okay, because of the change in the length. So here pressure P, here pressure P plus dou P by dou x into dx. Now if I have to talk about like forces here, so I will just multiply dA, whatever the small area of this fluid element will be there, correct? Just I will multiply with the dA. So that is what the pressure force is. Now we'll talk about the shear forces also. We'll talk about the shear forces. So then how the shear forces will be there, very important point, okay? Now see, if I talk about the shear forces, so let's suppose the flow is along this direction, okay? That is what flow towards from left to right. So shear force will be like this over this surface, okay, tau into whatever the small dA is there. So now remember this point, here I have taken the cross section area. Now in this case shear force will be acting over the element surface area, so that surface area will be different, right? Here for the pressure we have taken cross sectional area, but for the surface for the shear stress I will be taking the surface area of the fluid element, right? So that point is what very important. So what will be there, it will be 2 pi r into dx, the length of the fluid element, 2 pi r into dx. Now what is this small r? The radius of this particular fluid element, right? So let's suppose the radius of the fluid element is what, small r, but if I have to take the complete radius, okay, so it will be capital R. It will be capital R, okay? So the fluid flow taking in a circular pipe, okay, and that pipe radius will be capital R, but whatever fluid element I am taking, that is having a radius of small r. This much information should be clear, right? Okay. So this is what we can say, this is fluid element. This is what fluid element, right? So pressure forces we have seen, the shear forces we have seen. Now some basic assumptions we need to understand in the case of laminar flow through circular pipe. So what are those assumptions? See, First of all, steady flow. Okay, there will not be any changes with respect to a time. So steady flow I will be assuming here. Second will be what? It is what, see, the for a moment, like whenever fluid element I am taking, in that case I will assume a kind of a uniform flow, right? Okay, like uniform flow basically means the fully developed flow I am assuming here. Fully developed flow. So now what is the meaning of this fully developed flow? That everyone should understand, right? Fully developed flow. So what do you mean by this fully developed flow? Because actually what happens when the fluid actually enters the pipe at some few length, there will be a developing zone. Are you getting my point? When the fluid actually enters the pipe, so for a few length, let's suppose some entrance region, we can say there is some entrance region over which you will see flow is what gradually developing. After that particular entrance region, the flow is fully developed. Then after that you will not see any changes in the fluid flow. The fluid pattern is what same after the entrance region. So there will be some small distance entrance region that we called. During that flow will be developing. So I am not taking that part into our consideration. I am taking that part in which fluid is fully developed. There will not be any changes in the fluid flow pattern. Everything will be what, like same only. So fully developed flow, that is our assumption number 2. Assumption number 1 is steady flow. Correct. I hope this much point is clear. Now steady flow is there, fully developed flow is there. So for that assumptions, for these assumptions, basically acceleration will not be there, right? So what I will do here, okay, see, from Newton's second law, summation of forces will be equals to mass into acceleration. Simple. Okay, so as steady flow we have assumed, and fully developed flow, acceleration will not be there. So what I will be taking forces. What are the forces? Pressure forces, and other one is the shear forces. So P into dA minus P plus dou P by dou X dx into dA minus shear stress 2 into 2 pi r to dx equals to 0. Right. I hope the point is clear. Okay. So this was the equation. Now after simplifying, you will be getting what? Minus dou P by dou X dx into dA. Okay, and this term will go on the right side. So tau 2 pi r dx. Now this dA is the cross-sectional area of this fluid element. Cross-sectional area of the fluid element, right? So cross-sectional area will be what? Pi r square. R will be the small r for the fluid element. Right. Now if you just observe in this case, dx will get cancelled out, dx will get cancelled out, and this r will get cancelled out, and this pi value will get cancelled out. Now what are the remaining things will be there? I can directly say shear stress will be equals to minus dou P by dou X into r by 2. That will be our relation for the shear stress. A very important relation we are getting here. Minus dou P by dou X into r by 2. So this is the relation that we have derived here just now. Okay, so this relation we need to remember, very very important. Okay, very important relations we have derived just now. Okay, now from this relation we will conclude 3 important points regarding the laminar flow through circular pipe. Through that particular relation, tau equals to minus dou P by dou X into r by 2, from that relation I will conclude 3 important points, and that points will help you to solve some of the important questions in the GATE examination. Right? I hope that much is clear to everyone. Now, okay, what are those points? So point number 1, that you need to observe. Okay, before that point also, okay, let's suppose one by one we'll take it. Shear stress is proportional to R. Correct? So what kind of relationship it is? Linear relationship with the radius R. Linear relationship. Clear everyone? Linear relationship it is there. So tau proportional to R, that is linear relationship. Second point. What does this negative sign represents? What does this negative sign will represent? Tell me. Negative sign will represent that pressure decreases during the fluid flow. Pressure decreases during the fluid flow. That is what the point that we get understood from this one. Okay. Now you should be asking like, sir, why pressure is decreasing? Now, see, during the fluid flow, in this particular case is what we are understanding the point. Like during the fluid flow, some losses will be there. So for that, some energy will be what utilized. Some energy will be utilized to overcome the losses. Now, what are the energies available? So as we have assumed like a uniform flow, we have assumed, so velocity will remain same. So what kind of energy will be utilized? Only the pressure energy is available. So that pressure energy will be utilized to overcome the losses. Okay, that's why the pressure is decreases along the fluid flow. So negative sign represents pressure decreases along the fluid flow. Along the fluid flow. And the third point, this relationship is what valid? This relation is valid for both laminar and turbulent flow. I hope the points are clear. Yes or no, everyone? Please tell me first. So linear relationship. First of all, negative sign represents pressure decreases along the fluid flow. Then valid for both laminar and turbulent flow. Okay. So these points are what very important. Laminar turbulent flow, in both cases it will be valid because during the derivation of this relation, we have never assumed any conditions of laminar or turbulent flow. Right. So it will be valid for both the cases. Now as it is having a linear relationship, I can just draw the diagram here, how it will be varying. Okay. So I will just draw the diagram here so that you will understand. Okay. So let's suppose this is the pipe here, and in the pipe you can see. So let's suppose this is the center line. Now I will show you how the pressure will, shear stress will vary. How the shear stress will vary. Okay. So like this, shear stress is going to be what? Varying. Okay. Right. So this is the variation of the shear stress. Okay. So shear stress will be what? Maximum at the wall. Okay. Or you can mention shear stress at the wall of the pipe. I hope the point is clear. Shear stress will be maximum at the wall, right? Shear stress will be 0 at the center line of the pipe. Shear stress value will be 0 at the center line of the pipe. I hope the point is clear, everyone, right? So this point everyone should have a clear understanding regarding the linear relationship of the shear stress with the radius r. Okay, r by 2. Now in order to calculate tau max, maximum, or I can say wall also. So it will be minus dou P by dou X, that is what pressure gradient multiplied by capital R by 2. Because if you put R value as 0, that is at the center line, you will get the shear stress value 0. Correct. So this point everyone should remember. R will be the radius of the pipe. Okay, R will be the radius of the pipe. Clear? This thing. Okay, so very important points. Okay, so this relation is what very important. Based on the values of the radius and the pressure gradient, you can easily calculate the shear stress also. Now, some of the time what they will be doing, they will be directly giving the value of maximum shear stress, and they will be asking calculate the shear stress at some radius r. Okay, let's suppose total capital R, that is the radius of the pipe, is 10 centimeter, but they are asking the shear stress value at r equals to 7 centimeter. Radius is 7, but they are asking radius shear stress at radius 7 centimeter. So in that case, what you will do? So simple relation you can also draw here, like tau max divided by tau at any radius r. So it will be equals to capital R by small r, or from this you can write like this: tau equals to tau max into small r by capital R. This relation you can write. Okay, this is the general relation you can write. Okay, this is also one of the relation that you should remember. Correct. Tau max is at capital R, tau shear stress at small r. So tau value will be what? Tau max into small r divided by capital R. So that should be one of the formulas that you should write in your formula sheets, right? So formula sheets are like a very important asset for any GATE aspirant, right? So just before the GATE examination, you will not able to revise the whole subject through your class notes. So what you will do? Prepare the formula sheets, and from the formula sheets you can easily revise your subject, right? So that is what the importance of formula sheets. So I always suggest students to always create formula sheets for every subject, for every chapter. So your entire subject can be finished within 5 to 10 pages, and that 5 to 10 pages you can revise easily, and less time will be consumed in revising all those important relations. So formula sheet should contain only the important formulas, important relations that will help you to solve the numericals. Okay. So shear stress we have talked about. Now one more thing, guys. See, one more thing. So let us assume there is a pipe here. Okay. Pipe having let's suppose now pipe having a radius r. Let's suppose capital radius r it is they have given. Okay. Now at any section, so let's suppose any section, if I am taking, just for your understanding, I will take two different sections. Okay, so this is section 1, and let's suppose this is section 2. Now what I will do here, see, this is section 1, this is section 2. Okay. Now what I will do here, I will apply the Bernoulli's equation between section 1 and 2. Okay. So this is section 1, section 2. Apply Bernoulli's equation between one and 2, right? Between 1 and 2 I will apply the Bernoulli's equation. So between 1 and 2, what will be, how we can apply Bernoulli's equation? Simply pressure head I will write first of all, then velocity head I will be writing, then plus Z1, and then P2 by specific weight pressure head at section 2, V2 square by 2G, then plus Z2, then plus the losses that is there between section 1 and 2. So as the fluid moves from section 1 to 2, whatever the head losses are there, that I have taken here. Okay, so between section 1 and 2, right everyone? So if there any doubt, so please ask everyone. Okay, if there is any doubt, you should ask, right? So HF is the head losses during the fluid, as the fluid moves from 1 to 2. So HF means what? The losses. Head loss. Whatever the head is what lost as the fluid move from 1 to 2. Okay. So I hope the point is clear. Now what I will do here, I will calculate what is HF value here. Okay. Now see, this HF value will be what? See, if I just rearrange the values. So as the velocity is what same, because uniform flow I am assuming. Okay, I will write the point here for uniform flow. For uniform flow, right? So for uniform flow, so what will happen? This velocity term will get cancelled out. So only which terms will be there? Pressure head plus datum head. Okay. This is the pressure head plus datum Z1 minus P2 by specific weight plus Z2. Right, like this. Correct. So HF equals to this difference. What is this difference? Piezometric head difference. Pressure head plus datum will become what? The piezometric head. The difference of piezometric head will give you the head loss. That is what a very, very important concept in fluid flow through pipes. Right. Very important concept. So you should remember this one. Okay. So what I will write? Head loss equals to drop. Head loss equals to drop in piezometric head. Piezometric head. Okay. Directly you should remember this point. Head loss will be equals to drop in piezometric head. But what is the condition, guys? What is the condition for uniform flow? For uniform flow, right? So for uniform flow, whatever the head loss will be there, that head loss equals to drop in the piezometric head. Now, the case that I have discussed here, in that datum head is not there. So directly I will say what? Pressure head. So piezometric head will be there whenever the pipe is not horizontal. So if the pipe is horizontal, then that piezometric head will become what? The pressure head, simply because datum head will cancel out in the case like when pipe is what? Horizontal. So this again very important formula we have derived here, head loss equals to drop in piezometric head. This is a very, very important concept, guys. Please remember this concept. Okay, you should always remember this concept. That's why I'm writing here, very important. Okay. Now, any doubts till now? Any doubts? Please ask me. Is there any doubts? Please ask me, guys. So condition you should always remember, uniform flow, correct? So what we have discussed till now, like laminar flow through circular pipes we are discussing, and so fluid element we have taken, right? What are the assumptions? Steady flow, fully developed flow. Those points we have discussed. Now see what we'll do. I will do the velocity calculation part. Next part that I will do here is for the velocity calculation. Again, what we'll do, again take a fluid element here. Okay, so let's suppose another fluid element I have taken. Okay, like this, I have taken a fluid element. Right, so that is what our fluid element that I have taken here. So that fluid element is having a radius r, small r, and radius of the pipe is what? Capital R. This much information should be clear, everyone. Now, the first relation that we have derived just now is what? The shear stress value minus dou P by dou X into small r by 2. That is what the relation we have derived just now. Now, in this relation, that whatever we have written, HF equals to drop in the piezometric heads. So, in the horizontal pipe, as I already told you, like piezometric head converts into pressure head. So, in that case, directly you can write P1 minus P2 divided by specific weight. Don't need to write Z1, Z2 because pressure head, just the pressure head will be there in the case of horizontal pipes, right? Okay. So, this is the shear stress value. Now, one more relation we are having from the Newton's second law of, from not Newton's law, from it is Newton's law of viscosity actually, correct? So, that is what tau equals to mu du by dy. Now, y distance that we actually are taking from the fixed or from the solid surface. So, that y will be like this. Distance measured from the pipe wall will be what? Y. Now, I can easily write this y equals to capital R minus this small r. So, from capital R, if I subtract small r, I will be getting y, correct? So, now if I differentiate this one, what I will be getting? Dy equals to minus dr. Why r? Because r is what? Constant, no? Pipe diameter will be constant always. So, dy equals to minus dr value, correct? So, remember this point. So, I will be equating both the relations. Okay, if I replace dy with minus dr, then I will equate both the relations because the single variable will be there in both the equations, r, not y. Single variable will be there, r, right? So, if I use this thing, so I can directly write tau equals to minus mu du by dr. So, let's suppose this is equation 1, this is equation 2. Now, using equation 1 and 2, using equation 1 and 2, right? So, what I will be writing here? Okay, minus mu du by dr equals to minus dou P by dou X, that is pressure gradient, into small r by 2. Now, from this I can write du equals to minus 1 upon mu, okay, minus dou P by dou X into r by 2 into dr, right? This will be the equation. Now, I will integrate it, okay, I will integrate this one, correct? Now, if you integrate this one, what you will be getting? Minus 1 upon mu. Now, r square by 2 will be there. So, r square by 2 and 2 is already there. So, it becomes r square by 4 plus c. So, this is equation number 3, let's suppose. Now, I will be using the boundary conditions. What are the boundary conditions for this one? See, this is what very important. Okay, boundary condition at r equals to capital R, your velocity will be 0. Obviously, at the wall surface, velocity will be 0. That is what very obvious boundary condition we can say. Second boundary condition will be what? At r equals to 0, that is at the center line, your velocity will be maximum. These are the two boundary conditions that everyone should understand. Now, coming back to our analysis part. Velocity, we got this one. Now, we will apply the boundary conditions, right? Apply boundary conditions. So, if I apply boundary conditions, see. First boundary condition if I apply. Like r equals to capital R. Okay, velocity will be what? 0. Okay, so like velocity value will be 0 minus 1 upon 4 mu minus dou p by dou x. Instead of small r, you will be having capital R square, then plus c. So c value we are getting is 1 by 4 mu. Okay, plus this will become plus minus dou p by dou x into r square. Now very important point, you will be like thinking, sir, why you have attached the negative sign with dou p by dou x? Because dou p by dou x value is a negative, and if I attach negative with that, it becomes the positive. So that's why you should always, like here itself you should understand the point. This minus dou p by dou x is positive, right? Because the pressure gradient is what? Negative. Okay, so if I attach the negative sign with the pressure gradient, it becomes the positive. So if I have to write simply dou p by dou x or the pressure gradient, it will be negative, because during the fluid flow pressure decreases, so change of pressure will be negative. Change of pressure will be negative for whatever section we have considered. So change of pressure will be negative. So if I attach negative, then only it will become positive. So don't be confused like why we have put a negative sign here. Okay, so during the derivation we got the negative sign, and that negative sign will tell us pressure will decrease during the fluid flow. But minus dou p by dou x is a positive quantity, so never ever cancel out this negative sign during your derivation or the analysis part. Never cancel out the negative sign. We will simply attach the negative sign with dou p by dou x. Clear? Now, right. So these boundary conditions we applied, C value we got from equation 3. From equation 3, your U relation will be what? Minus 1 upon 4 mu minus dou p by dou x into capital R square. Okay, not capital R square, it will be small r square. Plus 1 upon 4 mu capital R square. Correct? I hope the point is clear. Now I will just simplify this relation, right? So if I simplify this relation, what I will be getting? 1 upon 4 mu minus dou p by dou x into capital R square minus small r square. That is what the relation we are getting, and this relation is what very important, guys. Okay, you should remember this relation, very very important. Now another relation. So now I will be putting, as I know at r equals to 0, you will be having U max. So your U max value will be simply 1 upon 4 mu minus dou p by dou x into capital R square. That is what your relation. Okay, again one of the important formulas you will be having. Now if I just divide both of these relations, what I will be getting? So if I divide both of these relations, what I will be getting? C, very important relation I will be getting. Like, okay, here I should write here U by U max equals to, so this 1 by 4 mu minus dou p by dou x will get cancelled out. You will be having 1 minus small r square divided by capital R square. This is very important relation, guys. Just with the value of r at any radial location, you can calculate the velocity if you know the maximum velocity in that case. Okay, so this is again one of the relation that everyone should remember. So see, in the laminar flow through circular pipe, there are a lot of formulas that we need to remember. So the only way that from which we can remember all these formulas, just to create the formula sheets in such a way that one by one all the formulas always it will be like a flow only. Okay, so when you will read, entire formula will be like remember for you. Okay, you can easily remember those formulas. So flow will be what very important. Like first we have discussed shear stress relationship, then velocity relationship, then after that some discharge relationship I will be writing, then some pressure gradient head loss formula, all those relations you should be writing in one paper itself. So that again again and again you will revise, you will able to remember all those important formulas. So then it will become very easy for you, right? So please like remember all the formulas are what very important. Any numerical can come and which one of the relation will help you to solve the question directly. If you don't remember the formulas or the relations, then it will be problem for you, right? Any doubt till now? Any doubts till now? Anyone please tell me first. Is there any doubt till now? Okay, now what I will do, I will calculate the discharge relation also. Okay, now again for the discharge, I will consider one fluid element here. Okay, so let's suppose this is our fluid element, right? Now, again same thing we will be assuming. This is small r, okay. This is capital R we are having. This is small r, this is capital R. Okay, so better we'll write it outside here. Okay, now see. Now I will be assuming a small elemental ring, and through that ring I will be calculating the discharge, and from that small discharge I will integrate over the complete pipe. Then I will be getting what? The total discharge. Yes or no guys? Please tell me first. Okay. So what we are assuming, consider small elemental ring having thickness dr, having thickness dr. Okay, so some small elemental ring we have assumed, and thickness is what? dr, right? Okay, now how to calculate the discharge through that ring? Very simple. Small discharge will be there, u into dA. Whatever the velocity will be there and whatever the radius will be there for that particular ring. Okay, so velocity relation we have already found out now. This is what we are having a velocity relation that I will utilize. That is what? 1 upon 4 mu minus dou p by dou x into capital R square minus small r square. Okay, dA will be like 2 pi r dr. Okay, dA, the area of your elemental ring, because thickness is what? dr, so 2 pi r into dr will be your elemental area of the your ring. Okay, whatever ring we have assumed here. Now discharge will be like this. Now we have to integrate this discharge from 0 to r, and from that I will be getting what? The total discharge, and from that total discharge I will be having one relation, okay, that I can use to calculate the overall discharge. Correct everyone? Okay, great. Now see, total discharge what will be like this? Integration of 0 to capital R, 1 upon 4 mu minus dou p by dou x, okay, into capital R square minus small r square into 2 pi r dr. Now this is what simple integration that you can do it on your own. I will give you just 1 minute to calculate this one and just tell me what will be the answers. What will be the answer? Everyone please tell me. calculate. Simple integration is there. Okay, so 2 pi again common part, 1 by 4 mu again common part, take it out of the integral, and minus dou p by dou x is also constant part. Okay, so take out of the, just take it out from the integral part. So r you need to multiply here, and this one also, it become r cube. Okay, and here it will be r into capital R square. Just integrate. Okay, so what will be the answers, guys? Please tell me first. What will be the answers? Okay, so to solve, finally pi by 8 mu into r to the power 4. So this will be the relation you will be having. Yes, everyone tell me whether it is correct or not. Everyone should tell what will be the correct answer. Pi by 8 mu into dou p by dou x into r to the power 4. That is what the discharge formula we are having. Now, through this discharge, we are able to calculate the average velocity, because I hope you remember this formula, discharge is equals to area into velocity. So that velocity is what average velocity. Always remember, area into velocity. In that formula, velocity should be average velocity. So we got the total discharge value, area we know, we'll get the average velocity from this one. Okay, so put it here like this. Area will be like pi into r square, and velocity, that velocity should be average. Okay, so now finally this v average velocity will be like, okay, see everyone, r square r to the power, it will get cancelled out and pi will get cancelled out. So here it will be 1 upon 4 mu. Okay, 1 upon 4 mu, not 4, it is already 8. Okay, not 4, it is 8. 1 upon 8 mu, okay, minus dou p by dou x, okay, then r to the power 2. That is the average velocity relation we are getting. Okay, now one interesting thing that you need to understand here is, like, what is the maximum velocity relation that we have found out? 1 by 4 mu minus dou p by dou x into r square. And what is the average velocity relation we have found out just now? 1 by 8 mu minus dou p by dou x into r square. Got it? Is this point clear? Now, very, very important point, guys. It is just half of the maximum velocity. That is what the conclusion we can draw from here. So, u average equals to u max by 2. Okay, for circular pipes. Okay, whenever you are having a laminar flow through a circular pipe. Okay, laminar flow through circular pipe. Through circular pipe. Got it? Now, average velocity relation we got. Now, using the average velocity relation, see what I can do here. Minus dou p by dou x, because average velocity is that important velocity parameter that usually we will use in the formulas, like in the calculation of Reynolds number also. Okay, while calculating head loss also, average velocity relation is what very important. Okay, so what is the average velocity relation? 1 by 8 mu. So what is 1 by 8 mu? We have forgot to write 1 by 8 mu. Correct? This is the point. Now, so what I will do, I will separate this minus dou p by dou x. It is like this, 8 mu u average divided by r square. Now this is the relation you should remember. Now if you remember, for a horizontal pipe we have derived, okay, what we have derived, see, I will show you again. For horizontal pipe, head loss is what, like P1 piezometric head, difference of piezometric head, that we have derived. Okay, okay, we have derived this one. Now using this relation, what I will be doing here, see everyone. Now here itself I will write. So let's suppose this is a pipe we are having. Section 1, section 2, section 1, section 2. So what will be the pressure difference, or minus dou P by dou X? Minus dou P by dou X. Like let's suppose this distance is what, L. This distance is what, L. So minus dou P by dou X, I can write like this. P1 minus P2 divided by L. P1 minus P2 divided by L I can write. Now P1 minus P2 is what, the pressure head difference, pressure difference basically. Okay, now this pressure difference I can, using Bernoulli's equation between 1 and 2, I can write simply it is the specific weight multiplied by the head loss. Because if you remember what you have written, what is the head loss? Head loss will be the pressure head difference. Got it? This much information everyone should know, how we are writing these things. Okay, this information everyone should know. Okay, because earlier we have discussed this thing. Using both of this relation, I got P1 minus P2 value as HF into specific weight. Yes or no, everyone tell me. P1 minus P2 value will be specific weight multiplied by HF. That is what the relation we are getting. Now instead of writing minus dou P by dou X, I will be using P1 minus P2 relation. P1 minus P2 relation I will be using. Now see. So again I will be writing so that there will not be confusion for you. Eight mu U average, okay, divided by R square. Now instead of pressure difference, what I will be writing, specific weight into HF divided by L. 8 mu U average divided by R square. So instead of writing R square, I can use D also. So it will be D square by 2. Basically, so D by 2 will be the R value. So D square divided by 2 square, that is 4. 4 will be get in the numerator part. Okay, that is a value of R square. So now from this one, what actually I am doing here, you should understand. I want to derive the head loss formula. Now the head loss formula will be like 8 into 4 will be 32 mu U average into length divided by W D square. This relation actually I want to derive here. This is the relation, very important relation, guys. And this relation is what actually the head loss. For laminar flow through circular pipe. Laminar flow through circular pipes. Correct? Yes or no? I hope the point is clear. Head loss for laminar flow through circular pipe. This is the formula that everyone should remember. Now, apart from this head loss formula, there is one more formula that we usually call by equation, Darcy-Weisbach equation. Darcy-Weisbach equation that we are using. Okay, that everyone should remember also. Okay, Darcy-Weisbach equation. Okay, that is what HF equals to FL V square divided by 2D into G. Now you should remember this formula is applicable for laminar or turbulent both. Applicable for both laminar and turbulent flow. Applicable for both laminar and turbulent flow, right? So applicable for both laminar and turbulent. So this thing is what very important, very important. Okay, so now using this relation also you can calculate, and using this relation you can also calculate based on the parameters or the information given in the question. Remember, in every formulas we are taking average velocity. So also in this Darcy-Weisbach equation, velocity is what? Average velocity, right? Please remember this point. It is not maximum or minimum or you can take anything. It is always the average velocity. What is F? Friction factor. Right. Now, and it depends upon the condition. It depends upon the condition whether flow is what, laminar or turbulent. It depends on that. Okay. Friction factor dependent upon the type of flow as well as on the nature of the surface of the pipe. So usually in the laminar flow it doesn't depend upon the nature of the surface, but in the turbulent flow it will depend on the nature of surface as well, right? Now as we are discussing the laminar flow through circular pipe, we can calculate this friction factor just by equating this relation and this relation. Are you getting the point? So using both the relation I can calculate the friction factor for laminar flow also. Okay, so HF relation from Darcy-Weisbach equation. So I will write same FL V square. So instead of writing V, U average I am writing. Okay, because both are same thing only. Just because I have written the formula of the laminar flow head loss like this. Like this. Okay. Now you can easily cancel out this L. You can easily cancel out this D and this D. Okay. So like this you can easily calculate. Now after putting all those values, you can calculate this friction factor. And please tell me what will be the friction factor after simplifying this relation. What will be the friction factor? Yes, everyone, tell me. Okay, friction factor 2 into 32 will be 64. Okay, 64 into this mu into U average divided by specific weight is what, density into G. Okay, density into G is there. We need to multiply 2 into G. So G will get cancelled out, and one diameter is already there. Okay. So just a minute, this U average will also cancel out, this one will remain there. So U average will come down actually. Okay, here it will be G only. Okay, and here it will be U average. Now this G will get cancelled out. So now finally your friction factor equals to 64 multiplied by mu divided by density into D into U average. Now there is a very important relation that everyone should remember. Okay, that everyone should remember, and that is what? The Reynolds number. What is Reynolds number? Rho into rho V, actually we'll write U average here, into diameter D divided by viscosity will be the Reynolds number. So if you just observe 64 divided by Reynolds number is actually the friction factor here. So this relation everyone should remember, very very important. And this friction factor will be valid for what? Friction factor for the laminar flow. I hope the point is clear to everyone. So friction factor for laminar flow, what we have calculated, 64 divided by Reynolds number. Yes or no? So see what we have discussed till now. What we have discussed. See, starting from this relation, starting from this one, laminar flow through circular pipes we have discussed, right? In that we have derived this relation, very important relation we have derived, right? And in this relation, three conclusion we have discussed, like linear relationship, negative sign represent like pressure decreases. Third, it is valid for both laminar and turbulent flow. So those points we have discussed. Then this linear relationship, right? And from that, this relation and this relation we can derive. Maximum shear stress will be always at the wall. And after that, one more thing we have derived, like head loss equals to drop in piezometric head. Very important in the numericals of the fluid mechanics. If you don't remember this concept, you will not be able to solve the question fluid flow through pipe. Simple. Head loss will be equals to drop in piezometric head. You will be always looking for like formulas, but this concept most of the time students miss this concept. From this concept you can easily solve the questions. You don't need much parameters like the formula that we have derived here, the head loss formula. Okay, if you just observe here, viscosity is required, most of the things are required, like, but head loss equals to drop in piezometric head will be valid for uniform flow. But the condition also you should remember, otherwise you will apply that formula everywhere. It should not be like that. Okay. So I hope laminar flow through circular pipe, whatever the basics part we have discussed, it is clear to everyone. Okay. In the upcoming sessions, we'll go beyond that also. We'll take the fixed plate also. Cout flow we can take, okay, in the upcoming sessions. So I hope this particular sessions will be like very much helpful for those students also, like who have never touched this particular topic in the college also. And whatever we have discussed, it is from scratch only. Like, okay, you don't need to remember anything. So you can watch this session and all of your doubts will be clear regarding laminar flow through circular pipes, right? So I hope you have enjoyed this session. Thank you so much.